So most of the work I've shown you so far has been focused on osteogenic differentiation. However, of course, the conductive materials we've been creating in our labs can be used for other tissue types. So Chinowich is a PhD student who's just graduated this year, and he's been creating an aligned conductive silk fibre mat for peripheral nerve repair. He has successfully prepared an electrospinning silk fibrin solution via a dialysis-free method. He then uses ethanol for treatment to create to increase the beta sheet formation, but this then results in quite brittle and fragile mats, so he then has to use a water treatment as a plasticizer to improve then the flexibility of those ethanol treated fibre mats. He then creates an interpenetrated and IPN network of silk with P.PSS via electrospinning, and he's shown that his electroactive mats are without toxicity, and when the conductive mats are coated with laminin in comparison to non-coated with laminin and comparative conductive mats just by themselves are significantly create significantly longer neurite extensions, and again they follow the alignment of the fibers. So with the electrical conductive mats versus laminin coated versus non-conductive scaffolds, we're increasing the neurite formation. And I also mentioned at the start of my presentation that I have a research interest in wound care. So my work today, as I mentioned, has been mainly focused on orthopedics, but I'm beginning to look at the benefits of electrical stimulation to wounds. And my PhD student, Maruna, has published a nice review in this area where we hypothesized that the well understood epidermis physiological current that is disrupted with a full subcutaneous wound may also be influenced by less understood influences of the electrical regime in the dermis, the underlying dermis. And this may also be influencing local cells such as macrophages and fibroblasts that are then important for the wound healing. Now we're looking at applying electrical regimes to influence the move of M1 to M2 macrophages in diabetic ulcers as a result, and to assist with guiding wound closure. And Maruna's published a nice paper where we could be modelling these microenvironments using finite element analysis to help guide us on what regime and conductive material could be used for this purpose to create this sort of electroactive bandage. And then a last word of caution for those working in this area. So my PhD student, Lindsay, has been looking at improving our analysis methods in this area. So we know that approximately 70% of the papers published in sort of bioelectronics in the sort of electrical stimulation on cells, including some of my own previous work, when we're using PCR as a tool to inform us about the selectivity, we've been using GAPDH as a reference gene. This reference gene, sometimes commonly referred to as a housekeeping gene. So Lindsay has looked at the top 6 reference genes using PCR to find the most reliable ones to use under electrical stimulation, and ones so that they're the ones that would differ the least. And she's looked at different seeding densities from 1 to 10,000 cells per centimetre squared. And she's used norm finder, delta-delta CT method and best keeper analysis to actually analyse the data. And we can see as a result, just looking at that bottom box there on the right-hand side, that GAPDH and actin beta vary with the application of electrical stimulation. So as such, going forward, we recommended using PPIA or YWAS as reference genes and not GAPDH, as this will typically skew the data that we're getting. So just to summarise my presentation today, I've shown you a variety of data showing that different types of electrical stimulus increase mesenchymal stem cell proliferation and osteogenesis. We've shown that the mechanism of the response is partly due to hydrogen peroxide low levels, but that this is not the only factor. And we know that some parts of the mechanotransduction pathway are also upregulated and are involved in the cell response to electrical regimes. I'm looking at the application of this in 3D using conductor materials and currently optimizing regimes and the design of those for enhanced tissue engineering and wound healing approaches. I'd like to say thanks to everyone in red highlighted here that's helped with this work, and also the funders and yourselves for listening. I'd like to give you all a warm welcome to come to Termis in 2023 that we're going to be holding in the University of Manchester. Very much looking forward to seeing you all there, and thank you all. I'm very happy to take any questions.
Thank you, Sarah, for such an amazing presentation, an inspired one. Lovely to see there's a lot of work led by PhDs, your PhD students, of course with your supervision, but very interesting and and complementary topics. So we can accept a couple of questions from the audience. Anyone would like to raise a question?
Yes.
Yes. Yes.
I'm very sorry, but we missed the end of the presentation, so we didn't clap because it was a fabulous presentation.
Thank you.
Yeah, we clap also online. So Jeffrey Mitchell.
We have a small problem with the internet for some reason this afternoon only. You presented many positive attributes for cells in applying electric field stimulation. I wonder if you have any information or guessing or that about whether there's any deleterious effects of applying electric fields, because obviously in applying the electric field you need to optimize the electric field, the pulse, the frequency, the duration, and optimization usually means there's some positive benefits and some negative benefits. I just wondered what the negative benefits might be.
Yeah, thank you. Very interesting question. So obviously, if you go too high, you know, you're going to nuke the cells. So yes, you're going to get irreversible electroporation of the cell membrane. And when I say too high, it doesn't have to be really, really high. So even when we're looking at, you know, 50, 100, 150 millivolts per millimeter. When you look at some of the literature, they've gone as high as 200 millivolts per millimeter, depending on the type of electrode that you used, depending on the size of the bioreactor, that can be okay. In the setup that I've been using with the L-shaped platinum electrodes, 200 millivolts per millimeter is just too high. And you can physically see, you know, the culture media kind of, it all goes white and it starts bubbling, and you can see that the current's too high. Temperature obviously could be too high, but our setup isn't an issue. It's the current that's important. So again, it's that electroporation of the cell membrane, and the different cell types will respond differently. So you get migration, for example, of the hemopoietic lineage versus mesenchymal lineages, and they'll be migrating to different anodes. So I've been obviously with autogenesis and the mesenchymal origin, very much looking at the cathode, but the anode is important for you know, macrophages and migration as well. So that needs to be considered. With the bacteria, so we saw with Carolina's work, the Staph aureus, of course, they've got a different cell wall. So, and they can very easily donate electrons. And so more similar to the mammalian cells. And that's why probably we're seeing the reduction of colony formation, because essentially you get the electrons being donated and then you get pushing away the bacteria and they just can't attach. That makes sense. So there's lots going on in the system.
If I could ask another question.
Yes.
Yes. In one of the very first graphs you showed of, I'm guessing it was in some cell proliferation test, I noticed that the effect of the electric fields stimulation was very different in different proportions of the time scale. Mm-hmm. And so therefore cells at a different point of multiplication or in growth have a different response. Is that something that's a real effect, or is it something that just comes from that particular test? I think it was the very first graph you showed that I don't remember what it was about now, other than it had a vertical axis, which I'm guessing was something positive, and horizontally was the typical 7, 14, 28 days.
This was the with the COMSOL model, with the difference in the current that's being applied through the system, or the actual cell response into that. Sorry. In
the cell response, it was like it looked like a plot of a standard cell proliferation test. Yeah. So maybe I misinterpreted it incorrectly, but it looked like that the last phase of it in the last 7 days was much more. The electric field stimulation was much more effective than in the first or in the second. And I wondered if there was any information which tells us about when's the appropriate time to apply electric field stimulation to cause the maximum effect.
Yeah, it's an excellent question. So there isn't a body of literature that has optimized that, because the number of experiments you're having to run obviously is huge. What we've been doing is working with a group in Bangalore and IIC in Bangalore with Hardik Pandya, who's developed a sort of a high throughput system. So I haven't shown the data today, to start looking at that sort of regime. So the amounts, so if it's 10 millivolts per millimeter versus 50 versus 100 on mesenchymal stem cells, and if we need to add a minute a day, 10 minutes a day continuous, and actually start to see the difference there. And I do believe it will make an effect. You do get an impedance build up within the system. So we're looking at a DC rather than being continuous, because it might only be those first few seconds that's important, and switching it on and off. And also alternating it. So not an AC current, but alternating the DC in terms of the path, if that makes sense, and moving those electrodes around. The graph I think that you showed essentially the accumulation. So I believe you're having an effect straight away, but then that's cumulative. So if you're already increasing, your stimulation, your electrical stimulated cells at the start, and that is ongoing, obviously you're going to get a bigger difference, that 7-day, 14-day, 21-day period. But I think there's an awful lot of optimization that needs to be done, and tweaking that can make a big difference.
Thank you very much.
Okay. Thank you. Is there any question?
Yes,
from yes, João?
So thank you very much, Dr. Cartmel, for your presentation. So I have a question regarding the work with the osteogenic differentiation of MNT, where you use a regime of 1 hour per day. My question is, have you tried longer times and see a better effect, or 1 hour per day was completely enough?
Yeah, what we have done, so the capacitive work that Joanne showed on the titanium, that was continuous. So that wasn't an hour a day, sorry, I didn't, that was continuous 24/7. And so we do get a result. But again, just similar to my last question, I don't know if we need that. I think actually we need shorter bursts, similar to mechanotransduction. It's whether or not we need an hour a day, whether or not we need 3 lots of 20 minutes a day. And that still needs to be optimized, I believe.
Okay, thank you. And do you feel there is any advantage of giving rest days, or having a rest day between the stimulation days? Do you think you can extract some advantage of that?
Yeah, I think that could be a benefit, because I think then the cell needs to respond to its stimulus, and then whether or not that's going to be readjusting its voltage gated ion channels and adjusting then its migration in response to that, and then you apply again. So those rest periods just to allow the cell to have the full benefit, if you like, rather than being constantly overstimulated. The work I've done so far essentially is to gain the proof of concept, and then to understand what's going on, if you like. So really understand the mechanism. But now we're starting to look at, because we know it works and we know things are changing. Now we need that high throughput system that I mentioned to really start looking at all those different options.
Thank you very much.
Okay, thank you. Any question from the audience? João, would like to raise a question?
Which one? Myself?
João Menezes.
I have just one, if I can. What you prefer? It's the decoupled mechanism, the direct coupled, or the capacitive coupled? Or if you have a preferred one?
Yeah, in terms of getting data in the labs from my students, both are great because they both work, right? We tend to do a lot of work with the directly coupled simply because they're easier and cheaper to make. What I actually prefer is the capacitive method, though, because what I'm trying to do is translate that through to clinic. And when I touched on the work with Joanne's work with the metal, I won't go into the intellectual property because there's other things I'm working on in terms of, having a device and capacitive stimulus on that, using a very cheap kind of battery, do you know what I mean? Just to have that DC stimulus to hopefully improve that osteoinduction. That's a bit more difficult when you have the direct coupled. It's a little bit more invasive for the patient. If we're looking for tissue engineering and just growing a scaffold in the lab, it depends on which electrode we're using. We use platinum. If you see in some papers that people have used carbon, and some people use stainless steel, some people have used gold. They have different Faraday byproducts. They'll have different effects on the cells. That needs to be understood. the platinum I feel is best, and it gives you the osteogenic data you need, without the toxicity that you might get maybe with a stainless steel electrode, but it's very expensive. Hence me again looking at capacitive, because you know, you can use stainless steel electrodes embedded in a polymer, and you can keep autoclaving that.
Okay, thank you. And let me just ask you last question. In our group, we are very interested in focusing a couple of our studies on developing numerical models, on digital twin models, to help to optimize cell culture experience. What do you envisage will be the future of combining this complementary approach? Can you comment on that?
Yeah, it's really exciting. It's going to be, well, it is the next phase, isn't it, that we're researching. And just as I was saying, in terms of optimization, it would just hugely reduce the number of experiments, improve our hypothesis that we're coming up with, and just make things more accurate. So yeah, it's very exciting.
Yeah, so we can talk in the next week or whenever you have a little bit of time to discuss some possibility of joint ideas. Okay, joint work. Okay, thank you once again. Thanks again, Professor Sarah Cartmel. Thank you for joining us, and we know we are following the Jubilees Day in England, so we know that it's an holiday, and thank you for joining us in this holiday in England. So we invite you to stay, but of course we understand if you need to go. Okay, we'll continue now. Thank you, Sarah, once again.
Thank you very much. Thank you, everyone.
Thank you. So Professor Jeffrey, do you want to lead now?
Leave?
Lead, share now.
Yes. Right, good afternoon to everybody online or here at CEDAR-SP. It's now my pleasure to introduce the next keynote speaker, which I believe is a composite affair. But we will start with Professor Paola Pascual Pereira, who is a multi-talented person. So she's Professor of Mathematics in the School of Technology and Management. She's a senior researcher here at CEDAR-SP. She's head of the multi-scale modeling laboratory, and an unusual accolade is she's PI of 3 FCT projects, all connected with electric field stimulation and modeling. So we look forward to your presentation, Paola, on numerical modeling impact in the design and development of tissue engineering systems. Over to you.
Thank you, Jeffrey. I don't know if we are, if you all are seeing my screen.
Yes.
Yes, so I might reduce this. Okay, all good? Yes, can you check? Yes, okay. So thank you once again for attending this session. This presentation is divided in 3 parts. We will start it by the motivation, discussing a little bit about the role of digital twins. Then Pedro Marcelino will detail the work that we've been doing around scaffolds. And then with scaffolds, and then João Menezes will present his work with bioreactors. At the end, we will discuss some future directions and conclusions. And I forgot to thank you, Professor Jeffrey Mitchell, for the kind introduction. So let's go a little bit back to where did we gain this inspiration. We had a chance to follow some of the previous past works that Professor Sarah shared with us. Our inspiration came from some similar works but these works were performed with exploring a new technique to help kids from a pediatric hospital in Portugal that, for instance, with 11 years old, didn't know how to write and read. Why? Because they had a paroxysmal epileptic activity during the sleep. So at the time, this epilepsy was they could not be get a surgery because, for instance, some of them had the epilepsy. Are you listening?
Yes.
Yes.
Okay. They had the epilepsy in, for instance, in the language region in the brain, or they had more than one epileptic focus, and so they were refused for surgery, or, for instance, and there are also no medication for treating this type of epilepsy. So they didn't have convulsions, but they had this paroxysmal activity while sleeping that didn't allow them to develop cognitively. So we were challenged by a neurologist in Hospital Dona Estefânia. He wanted to optimize application of this electrical stimulation technique. For doing that, we had to develop, and starting by simple brain head models, and we had to and then we go through more realistic ones, and we had to optimize all the biophysical parameters involved, and we were able to define and we were able to define some guidelines to apply these in the hospital neurology department, especially our study focusing this application. So for creating better and better models, we had to get some results and some data from the experimental models, either in vivo and also in vitro, from the in vitro, and also from the different literature review available. And so we got at this time, and for this application, we got very interesting results. And in fact, this work lead to a prize for the Portuguese National Neurology Society, because these results and the combination of these mathematical modeling with these experimental models lead to obtain an optimized technique to apply to this concrete problem. And so we were very inspired by this work. Therefore, we decided, and back to the work that was being developed in CDRSP, we decided to use this analogous approach, but for tissue engineering issues. And so, what is the role of this kind of numerical model, digital twins, for instance, in industry? This virtual in silico representation, acting as a real-time computerized counterpart of living entities, physical objects and process, can revolutionize the industry. This digital twin concept is one of the main concepts associated with Industry 4.0, and it's these first digital twins first appeared in the aerospatial field. Its first definition was done by NASA in 2010. So we have the physical model and also the virtual one, and so this dialogue between both can help to obtain a virtual model that mimics better and better the physical one. So, advantage of digital twins in biomedicine. So we have integrating molecular, clinical, and imaging data through computational models will allow to generate a digital twin of each patient. And we all know that this is a very high complex system. So eventually, when you talk about human body, we are talking about 1,000 billion cells. For instance, when you address the spatial shuttle model, we are talking about 100 million parts, which is also a lot. But look at the amount of cells when you're addressing the human model. So treatments can be first applied on digital twin, and the best options selected for the treatment of the real patient. So likewise, this allows the personal prevention pathways can be designed. Both approaches optimize patients' outcomes while minimizing costs, as patients will not receive unnecessary treatments. And so we can have better therapies, promoting well-being, have a personal solution, saving costs. There's a lot of advantage. Regarding the personalization, for instance, we can think about this way. An individual patient has a local sign of disease. We can see here in red. So we can create a digital twin of this patient, and we can construct unlimited copies of these models. So based on computational network models of thousands of disease relevant variables, we can check for instance, all the different medications that could solve this problem. And so each digital twin is computationally treated with one or more of the thousands of drugs. So this can result in a digital cure of one patient. So we can see here, so we find this solution, and so this solution can address this problem. So the drug that has been effect on the digital twin is selected for treatment of the patient. And so this approach can contribute to an enormous and lead to an enormous gain. So what are the main advantages? Rational optimization of experimental protocols, procedures, replacing the traditional try and error approaches. So computer numerical models can be used to predict experimental outcomes and develop mechanistic relationships, avoid unnecessary experiments and reduce costs, and replace and minimize animal testings, being compliant with the 3 R's principles: reduction, refinement, and replacement. So our motivation for addressing all this methodology to tissue engineering, total fragility fracture in Europe are estimated to increase from 2.7 million in 2017 to 3.3 million in 2013. So we all know that, and the resulting annual fracture-related costs runs from 37.5 billion in 2017 and are expected to increase to 27%. And we all know that there's a European earthquake, and it has not reached yet its highest magnitude. And so there will be a lot of fractures. For instance, when you're thinking and focus only in bone fractures, there will be, this is an enormous problem. So there is the traditional approaches for dealing with these bone defects that might occur after trauma, infection, or oncologic resection. So when we're talking about small bone defects, usually heal without complex interventions, but critical size defects more than 2.5 centimeters will require secondary procedures to obtain union and healing. So the common practice runs from autologous crafting, induced membrane technique, bone transport through destruction osteogenesis, and free vascularized bone transfer. So all these approaches have disadvantages. We want to focus our study in these in the tissue engineering approaches. So tissue engineering approaches focus and related to fractures recoverable problem include the culture of stem cells seated on a bone scaffold for cell growth and differentiation of bone cells in an environment that mimics the native tissue for posterior patient implantation, promoting local fracture healing. So to increase cell rate and time of survival during the in vitro phase, the culture medium must be periodically replaced to supply nutrients and or growth factors to cell and removal of toxic cell by products from the culture to avoid cell necrosis and limited extracellular cellular matrix formation. So traditional in vitro studies are empirical, perform being time consuming and highly expensive. Numerical models can help to understand the behavior of cells, allowing to recreate studies where we can block some variables and others are kept constant. The inclusion of these new biophysics and bottom-up approaches of cell culture can play also here a key role, and that's where we are focusing now our studies. So we are developing these digital twin models, considering scaffolds and considering also an optimization of new bioreactors. And we are also focusing our study in optimizing the mechanical and electromagnetic stimuli in these complex systems. So I'm now going on to pass my my word to Pedro Marcelino. Pedro will talk and present his work related to the scaffolds, manufactured scaffolds that we produced in using additive manufacturing. So Pedro, please, you can share your work. I think Renato might
start the video. Is that what you're saying?
Yes. Okay. So, but Pedro, I might, as the internet is not working so well, I might try to help and present the video. You send it today, right?
Exactly.
1 minute. If you, yeah. Okay, 1 minute. Let's see where it is. It was today, Pedro. No.
That's
Okay,
the video, but
it's here.
I think I think we do not hear.
No, I found it. I'm just downloading it because sorry about this delay, but as the internet is not working so well, let's try to open it here, and I can share with you the video.
Should I try to reproduce the video in my computer?
Yes, if you believe this, it will work.
Okay, let me try.
Thank you, Pedro.
Okay. Let me share. Let me try to find. Okay, do you all see the screen?
Yes.
Okay, then tell me if you all hear the sound.
Okay, thank you. We are not hearing Pedro.
Sorry.
Pedro, I
Okay.
can share, okay?
Okay.
It's here. Okay, sorry. 1 minute. Mhm. Please check if you are seeing.
Yes, that's the video. But again,
We just can't hear.
we just okay. No one is hearing it. No one is hearing the sound.
Professor Paula,
Mm.
make sure
Yes.
you are sharing the sound also with the image. Yeah. There will be some option with in the Zoom to share the image and sound.
Okay. Mm. Okay, I found out.
Okay.
We'll start again. Please check.
Hello, good afternoon, and thank you for the opportunity to talk about the work we have been doing.
Yes, it's okay.
For the design of curved scaffolds and also for the characterization of their behavior, all in the context of osteochondral tissue engineering. So to start, let me give you a brief context. Osteochondral tissue is a tissue located at the extremities of long bones. It is composed by articular cartilage, calcified cartilage beneath it, and again, the subchondral bone. It displays an hierarchical structure, and that hierarchy can be seen in terms of composition, cell morphology, metabolism, and also mechanical properties. And a fine interplay between all these components is necessary for normal functioning tissue. However, due to limitations in the healing capacity of articular cartilage, defects can aggravate with time and lead to the development of degenerative diseases. Depending on the severity of the injury, several approaches can be taken. However, none of them is fully capable of restoring the tissue native functionality. And so in that sense, tissue engineering presents itself as an alternative for the development of new therapies. When you think of tissue engineering, you think about cells, either native cells or stem cells that give rise to cells, to those cells. Also think about bioactive factors, which are more chemical signals or physical signals that are sensed by the cells and can be used to modulate their behavior. You also think about scaffolds, which are the structures where cells are seated and are also necessary for them to grow. We also think about the bioreactors, and those are the vessels that we can use to grow cells and also to provide them the stimulation. Because we are trying to create scaffolds via extrusion printing, here are some examples that we find in the literature. So those scaffolds usually have this grid-like shape. They have a cylindrical or cuboid structure that you see here below. And so that gave us the motivation of trying to create a scaffold that would mimic the native curvature of the tissues, and also in order to present a more patient-tailored alternative for when creating scaffolds for tissue engineering. Here we have an important site where it would be relevant to create curved scaffolds, and that is the human femur. On the extremities, it's where we have the osteochondral tissue, and as a first approach, for the sake of simplicity, we started by trying to create scaffolds that would follow the curvature of spheres that would approximate the curvature at the extremities of this bone. So again, here we have the situation. We have again this explanation of the process that we are trying to implement. So to the left, we have one of the spheres from the previous slide, and we were trying to create a scaffold that would follow that curvature. Because we're going to use FDM printing to create these scaffolds, it was more convenient for them to have straight sides. And for that reason, we do a cutout in this sphere and then print scaffolds with following the shape of this cutout. And I mentioned convenient for the scaffolds for osteochondral tissue would be about 2 centimeters, and so for that reason this cutout was designed to have more or less that dimension. Another consequence of the manufacturing process that we chose was that instead of printing the scaffolds laying on one of their larger sides, it would need to be printed on one of the smaller sides, again because it was going to be curved and because we didn't wanted to use any kind of support structure. Here to the left we have a cross-section view of one of the developed scaffolds, and here it shows us one of their characteristics, which is that when you go towards the bottom or towards the top, the fibers of the scaffold start having less and less support. And because we didn't want to use any supports when you printing the scaffolds, that creates us a limitation, and that gave us then a design objective, which was then to determine with which radius we will have this limit situation between adjacent fibers of the scaffold, and that is seen here to the right. So the situation that we wanted to achieve was that that we consider that was necessary so that the scaffold would be printable, was that we'd have this tangential contact between the successive layers, adjacent successive layers of the scaffold. And so that gave us a design objective. So here on this slide we have a systematization of the problem that we wanted to solve. So here again we have some dimensions relevant for the scaffold. You have here on the left is L, which represents half of the height of the scaffold, so it's distance from the center of the scaffold to the bottom. We have an R, which gives us an idea of the curvature of the scaffold. We have a dimension relating the horizontal distance between these 2 points of successive fibers of the scaffold. We also have a distance relating the vertical height difference between these 2 points in successive fibers of the scaffold. And here to the right we have the equations relating all these variables. Because we have 5 variables, we have 3 equations. If we assign values to 2 of them, we are in conditions of solving the system. Due to the way the problem was proposed, we had already assigned values to 2 of those parameters. So L is half the size of the scaffold, so that means that we'll have a value of 10.05 millimeters, and also the distance, the horizontal distance between consecutive fibers, so that we have this minimal tangential contact between successive fibers of the scaffold. Then because of the dimension of the fibers, it gives us that this distance is 300 micrometers, and so we are in condition of solving the system. We use two methods to solve this system. We use the design software, and we also use Mathematica, which gave us an algebraic solution to the system. And satisfyingly, both of the solutions gave us the same result, which was a radius, a minimal radius, so that we could have the minimum tangential contact between adjacent fibers of, again, the radius of 13.79 millimeters. However, there's one more operation that we need to do, which is to have a dimension that can relate us, to have a dimension which is relative to the curvature of the scaffold and not dependent on their dimension. So the calculation that we did previously is concerns to the situation that you have here on both sides of the scaffold. So on this side closer to us, on the one, and also on the one farthest, because that's where you first find the situation where they start not having contact between the adjacent fibers in the scaffold. And so for that, so that we would have a dimension that would be only relative to the curvature of the scaffold, we just have to use the Pythagorean theorem to determine the radius of this circle that goes through the center of the scaffold. And doing that, we get to a radius of 17.064 millimeters as the minimal radius, with which we'll have minimal tangential contact between successive layers, and also considering that the scaffold will have a side of 20.1 millimeters. Because we are using a parametric design to create the scaffolds, we would only need to give it the dimension of the radius, and then the software would create for us scaffolds with the desired curvature. And that's for that reason we chose to print the scaffolds, to design and print the scaffolds that you see here on this slide. So in the middle we have the limit situation. To the right we have a scaffold with a higher radius, and to the left we have a scaffold with a smaller radius. And in the bottom we have the pictures of the scaffolds that were produced by FDM printing using PLA. Here, to confirm our predictions, we did some micro-CT imaging of the scaffolds, and here to the left we can confirm our expectations. So to the left, with the 14mm radius scaffold, we start seeing some fiber detachments and also some deformation of the scaffold fibers. In the case of the 17mm radius scaffold, we see some detachment of fibers, again on the extremities, and that is something that we did not notice in the 20mm radius scaffold. And again, this is something that is in line with what we expected from the design. Something that we also tried to do was to predict the mechanical behavior of the scaffolds, and for that we used finite element analysis. Because this scaffold models were very complex, we were not able to do it to the entirety of the model, and for that reason we chose to do it to smaller sections of the model, which shows 3 sections: one central section, one section in the corner, and also a slice through the center of the scaffold. And the way we did the simulation was to think of a load that would be applied on this face that we see here, and we were considering that the back surface was considered static. So starting with the center section, to the left we have a side view of that section, in the middle we have a front view, and to the right we have a top view. What the model told us was that the higher stresses would be predicted in the intersection of the scaffold fibers. So that would mean that the highest stresses would be seen here in this intersection between these fibers, again over here, and again always in the intersection is where the model predicted the highest stresses. Also on the side, comparing the side where the load was applied and the side which was fixed, higher loads were also predicted on the side where the load was applied. It also predicted that the fibers which were in the direction of the applied load would have higher stresses when compared to the fibers that were perpendicular to the applied load. So that means that fibers in this direction have higher loads than these fibers in this direction. Moving to the corner section, so again a similar situation. Higher stresses predicted in the intersection of the fibers, higher stresses predicted on the side where the load was applied, and also higher stresses predicted in the fibers which are in the direction of the applied load. And again, the same thing was seen in the slice through the center. So here this slide is just summarizing all the previous results, again repeating the conclusions that I've showed in the previous slides. So with this work we were able to conceptualize and develop 3D printed scaffolds, curved scaffolds for personalization of osteoporotic tissue engineering approaches, we're able to manufacture and characterize 3D printed curved scaffolds, and also to predict their mechanical behavior using finite element analysis. To finalize, let me acknowledge the financing entities that allow us to do this project. And with this, I finished my presentation, and I'm open to any questions that you might have.
Sorry, Professor.
If you're saying something, Paolo, you're muted.
Sorry, I was saying yes, thank you. I was we just sharing now the part from João Menezes. So now we will he will share with us his work related to the bioreactors research. Okay, 1 minute. Here. Okay.
So, good afternoon. I will present to you bioreactor digital twin concept, and as it is an essential modeling tool, or can become an essential modeling tool to estimate local environmental conditions and experimentation zero. And this model can impact the design and operation of tissue storage system. As you probably are all aware, tissue engineering promises to correct defects on organs or to cure diseases based on the concept that you isolate precursor cells from the patient or from other original lines, and then you grow them and mature them in an in vitro environment. You give all the proper of the required conditions, like a supporting scaffold and also electromagnetic stimulation, nutrients, and many more. Until the tissue grows and proliferates and differentiates into the mature tissue that you are interested in, and then you do an in vivo culture and you implant that tissue on the patient to correct the original defect. So our goal was was about this in vitro phase, and to understand in bioreactors how are we delivering electromagnetic stimulation regarding bone cell cultures. So this on your right part of the screen, you can see 4 kinds of delivering of the electric field delivery based on the electrode position. If it is inside the culture medium, you have a direct current, and if you have them outside of the culture medium, you have capacitive coupling or a semi-capacitive coupling. If you have one electrode inside and one outside, and if you use elements coils, you may have an inductive coupling where you have a magnetic field that induces an electrical field on the cells. So to understand this, we try to look into bioreactor construction and all the things that they require to give to the cells in order for them to grow and differentiate. So bioreactors, they require a very complex multi-parameter control process capable of delivering an adequate cellular environment, as I was told you, to promote cell culture, cell growth and differentiation into the desired tissue. So you have to give all these properties and many more. This is just a small sample, but you have to give nutrients. You have to, of course, provide a culture vessel. You have to control the osmotic pressure, the temperature, the pH, the growth factors. You have to remove cell waste, also provide adequate stimulation and control gas diffusion. And all these conditions have to be done right in order to obtain a major tissue that you are interested in. But very recent studies, they are calling for best practices in this control. You have here two articles, one from this year and the other from the past year, and I will read a sentence to you from one of them that I think it's very self-explanatory. So, in biomedical studies, the environmental conditions used in mammalian cell cultures are often underreported and are seldom monitored or controlled. Best practice standards are urgently needed. So, the problem is that it's very hard to compare if you use different conditions. If you use one different condition, it starts to be very hard to compare. If you use many, it's practically impossible to do it. So better practice in reporting and in the operation of bioreactors are really needed right now. As I was told you, this comparison and replication problem, it's a common practice. It's very hard to address. And so, as you see, this is just a small example. We have here 3 different bioreactors on the top. Also, we have 4 different kinds of electrical stimulation. We are just looking for electrical stimulation. And if you had different designs with different protocols, and if you also had different culture mediums, different environments, different scaffolds with different topologies and different materials, and also different setups and protocols and different cell sources, you have lots of differences. And so here is the problem. It's very hard to understand which conditions you are generating in your design, and also very hard to compare your experimental protocols with one another groups. And so this whole area is having real problems in replication and in understanding human science himself. So a solution is needed to allow comparison and translation of protocols among different setups, and one solution that also allows to control and predict the stimulation delivery, if we are talking just about the stimulation part. And our proposal will comes to a digital print solution, but how? So we start with a central bioreactor design with its CAD file, and with that CAD file we do 2 things. One of them is we print it, so we use the CAD file for a physical part, so we use direct digital manufacturing, namely FDM technology, and so we design our bioreactor to be completely 3D printable, open source for science purposes, easily fabricated and customizable, and with highly reproducible and modular configurations that can be adapted and further evolved for different purposes and for different labs and research capabilities. And with the same CAD file, we also use it to do a virtual part. So we use it to do a digital twin numerical model. So in one of the parts we construct the bioreactor, and the other we predict how is the bioreactor generating conditions inside of it. So this digital twin numerical model contains electromagnetic, thermal, and fluid dynamic models of this bioreactor for improved understanding of the local conditions that it generates at the region of interest, so in the central part where the cell culture occurs. So this improved bioreactor cell culture control is achievable with this technique. In the end, if we sum the 2 parts, we have a tissue engineered bioreactor with improved experimental comparison and replication. So you can share the design, you can share the 3D printing, that configuration, and you also can share the digital twin model among scientists in order for better replication and comparison of results. Oh, this is all very pretty, but so how can we use this digital twin concept to our advantage? This is the thing that you probably are asking. And I see three main ways, at least, that we can do this. So the first advantage is we can predict local solar environment conditions accordingly to external inputs, like peristaltic plant flow, electromagnetic wave generators of sources, and we have done this on one of our first works. So this is on the top you can see the first version of our bioreactor. This was published on Polymers with this title and multimodal stimulation cell-coupled bioreactor for tissue engineering and numerical modeling approach. And we combined a perfusion bioreactor with a direct coupled electric stimulation. This is a modular design, and also so we translated the stimulation protocol from two studies from other researchers into our design. So we could replicate their conditions in our designed bioreactor. So this is a translation and replication that I was talking about. So we understand the specific electrical inputs and flow in light properties needed to replicate those studies in this particular design. And we achieved this, so you are seeing here COMSOL simulations of the digital twin part, and on your left side you see the electric currents physics model, where we try to replicate the Molbini et al. Protocol at 100 volts per meter. So we know that in our design this is needed to have an input of 0.8 volts between the electrodes to achieve that experimental conditions. And on your right side, in the fluid dynamics models, laminar flow, we know that we require to achieve 0.5 to 5 millimeters per minute. This is a condition used for obtaining massive mineralization in another study, and this conducts us to an inlet in our model, in our design of this velocity that you see here on the top of 1.14 times 10 to the minus 4 power meters per second. So these two models allow us to translate protocols from other research groups into our design. So this was the first advantage. The second advantage is to predict. We can, with this approach, we can predict the influence of the scaffold geometry in the delivery of the electrical stimulation in our case. So we have done this also and presented this on a conference, in an MBC conference. And what we have done was we take the Brighton et al. Capacitive couplet setup that you see here on the image. We place there an orthogonal scaffold, and we observed what happens in these three blue regions. So we use EASE protocol, so a 60 kilohertz wave. It was a sine wave, 44.81 volt amplitude, and this generates a 2 volts per meter electrical field on a culture medium if it is empty. But if we add something to it with a scaffold with a conductivity, with a different conductivity than the surrounding medium, the conclusions are different. And so what we saw was this: if we observe that three regions, that we one outside of the scaffold, one in the interface between the medium and the scaffold, and the other inside the scaffold, just you are seeing this on the screen, but using the same stimulation protocol and the same culture medium electrical properties, but just changing the material of the scaffold from exactly controlled scaffold is equal to the culture medium, but thermoplastic scaffold, hydrogel scaffold, and the metallic scaffold, you see that there are very different properties. When we use a more isolating scaffold material than the culture medium, it generates local hot zones and cold zones inside the scaffold, and you can amplify and attenuate your stimulation locally, as you are seeing on the second and third column. And if you have a more conductive scaffold than the culture medium, the material completely shields your simulation, and you have a surrounding electrical field of almost nothing, because your scaffold will do the electrical conduction himself. So this is a very interesting result, but from the simulation part, another advantage is that you can use your numerical models to understand the simulation protocols applied by other experimental setups, predicting their simulation output and comparing it with the reported values. So you can use models to validate what other scientists are doing. And in our case, we look at 8 different tissue engineering capacity coupled simulation systems. We run models according with geometry that they reported, and we do that by 3 different types of modeling. So we do an equivalent electronic circuit model, we do a finite element model, and we do also an equivalent electronic circuit, but solved not analytical, but with the LT-SPICE solution. And what we do, we compare the predicted values for the electrical field magnitude with the reported value for electrical field magnitude. I have to say that this is not, these scientists, they didn't measure the resultant electrical field. They also estimated the resultant electrical field, and so what we find out was that their estimation versus our 3 different independent estimations, only 3 of them agree with our predictions. Electrical field, 5 of them completely disagree with our electrical field magnitude predictions, and usually they overestimate, and we pointed out what was the mistake. But I want to leave this with a small take-home message. So model-guided design of capacity-coupled systems based on a solid theoretical background is necessary to ensure reproducible protocols for successful translation to clinical application in tissue engineering. Because all of these scientists see results from applying electrical stimulation, but many of them effectively have much small electrical field magnitude than the one they were predicting. So this is very important in order to compare results and to understand what is really doing, what electromagnetic effects are really happening in the cell cultures. So you can use models to validate other setups and other conditions. Finally, saying that a future vision for this part. So I showed you a bioreactor model, a scaffold model. We can see we are looking more to electromagnetic simulation, but you can look this to fluid flow perfusion, to thermal models, and maybe in the future into a cellular tissue model. So starting to place like an agent-based modeling or other techniques that you can make some biological rules. And if we find a way to get all the models together and mix them up, we may have and reach very interesting conclusions into some new protocols, and maybe reveal a little bit more about this process of cellular differentiation and cellular proliferation. So finally, leaving you with 4 bullet points. Numerical models should be considered as a standard tool in tissue engineering to predict the delivery and evolution of local cell culture conditions inside bioreactors. They also can be used to recreate other stimulation experimental works and adapt them to different bioreactor designs. Understand and fine-tune stimulation protocols previously to their experimental application will lead to fewer errors, may lead to new discoveries of undercover processes in different cellular lines, and also sharing the experimental setup and model, CAD plus construction and numerical model methodologies have the potential to increase experimental repeatability, while creating a common platform among researchers to compare results, update protocols, and understand underlying biological mechanisms. So thank you. I will be ready shortly in the end.
Okay, thank you. Thank you all. Thank you all. We are running out of time. Just as very quickly, thank you for all the team. The team involved here, for Professor Frederico Ferreira from DBB in US Technical University, Professor Pedro Miranda, also all the students, all the researchers with us, also Federico Barbosic is not here, and Abias Dacta from the City College of New York, and the 3 FCT projects involved here in this research. So we have time now for one question, last very briefly question, because we are a little bit running off time. Sorry about this delay. Is there anyone who would like to ask a question?
Questions? Yes.
So thank you very much for the presentation. I just wanted to ask, so it's really interesting to be able to make the bioreactors fine-tuned for the applications we want them, but well, it's for you, the question. So just how big can you make it? Because precision engineering needs really a lot of cells. So how big did you test these bioreactors? We didn't get it to test it yet, but we are thinking about having 4 samples per bioreactor. So this is our time. But I think you can expand them, because if you can really print them, you can make lots of them, and you can make them self-contained. So have heater elements inside and possible gas diffusion inside. So of course, you cannot grow the thousands of scaffolds, but you can grow maybe for maybe 10 or 20 per bioreactor, I think. Okay.
So you could consider a kind of a scale-out strategy instead of the scale-up. So doing in parallel many runs instead of doing the large vessels.
I see. I'm thinking about multiplying the same element many times. So I think one like doing 4 samples, but having 10 of them. So I can 4 times 10. But at this moment, I think I see what you mean. But once we are doing very small cultures, I don't know, 10 milliliters per 10 milliliters per 3 milliliters is the size of the regular scaffold. So I don't think growing, because you change the conditions by a lot, and you have to keep
large bioreactors that were well controlled, that were reducing kilograms of material. So I think some of it is our adjustment and understanding of these procedures, as well as incorporating the things which are special to tissue engineering. So, Paola, thank you very much. And back to you.
Okay,
the person in charge.
thank you, Jeffrey. We are now moving on to our next speaker, Diogo Nogueira from the Institute of Bioengineering, Bioscience and Technical Institute of Technique in Lisbon. Diogo is a researcher associated at the Instituto Superior Técnico, where he obtained his PhD degree and master degree in biomedical engineering. So today he's going to give a talk, keynote talk entitled Development of a High Density System for the Expansion of Human-Induced Pluripotent Stem Cells as Aggregates in Single-Use Vertical Wheel Bioreactors. Thank you, Diogo, for accepting our invitation. You can start it. Thank you.
So thank you very much for the kind introduction. Thank you all for being here. Thank you for this opportunity to present my work. So I am Diogo. My work is entitled Development of a High-Density System for the Expansion of Human-Induced Pluripotent Stem Cells as Aggregates in Single-Use Vertical-Wheeled Bioreactors. I obtained my master's degree in biological engineering from Technico, and I've developed my master's thesis at the Stem Cell Engineering Research Group. Then I did my PhD in bioengineering at the same institute, and now I am a researcher over there. So I work at IBB, the Institute for Bioengineering Biosciences, which combines an understanding of the complexity of the living systems with engineering approaches, and in order to foster the economic growth of biotechnology in Portugal and for transfer knowledge to society. And so we are divided in 4 groups: the bioengineering research group. Can I use a pointer? Yes. Usa para apresentação, para ver online. Vamos escrever um rato. Ainda assim.
Queremos. Mas só tirar isto. Só segurar este. Okay, pronto.
Thank you. So we are divided into 4 groups: the bioengineering research group, the biological sciences research group, the stem cell engineering research group, and finally the biospectroscopy and interfaces research group. The work I'm presenting today is from this laboratory, which I'm in, the stem cell engineering research group. And the goal of our research group is to achieve new developments in stem cell-based therapies and treatment options and diagnostics by stem cell bioprocessing. So we are located at Instituto Agrotecnico and Tax Park campus, and we have 3 different focus areas: the biology and engineering of pluripotent stem cells, the development and manufacturing of cellular and molecular therapies, and finally, biomaterials and devices for advanced medicine. And the work I'm presenting today is from this focus area. So starting off with a bit of Greek mythology, here you have Prometheus, which was punished by Zeus and was chained to a rock and had his liver eaten every day by an eagle, and every night it would regenerate. And so we can think of the goal of regenerative medicine to do this precisely so that every one of us can be Prometheus. Because in fact, we have a lot of issues to tackle nowadays. For instance, looking at cardiac diseases, cardiovascular diseases are the leading cause of death in the world, and have been for many years now, even considering the numbers of the COVID-19 pandemics. And so, for instance, considering the heart diseases, we definitely need new solutions to this problem, as given the prevalence of the risk factors, their mortality is only expected to increase. And so, one solution that might linger in the horizon is stem cells. Stem cells can self-renew, generating identical copies of themselves, but they can also differentiate into many cell types. So we can try to generate partial constructs or even whole organs. Stem cells come in all shapes, sizes, and potencies, from the egg, which is a totipotent cell, can generate all cell types of the body, to multipotent and unipotent cells, which can only generate a limited number of different cell types. Pluripotent stem cells in particular can generate all cell types from the human body, but cannot generate a whole individual by themselves. And so they are very promising for these therapies. Embryonic stem cells are pluripotent, but they have a problem of being generated from embryos, thus requiring their destruction. Whereas human-induced pluripotent stem cells can be generated from somatic cells of an individual, thus they do not require the destruction of the embryo and can overcome many of the ethical issues of embryonic stem cells. Moreover, they can be generated from patients, so we can use them for a personalized medicine approach, using the patient's own cells in order to check drugs that are adequate for that patient, or we can use them for transplanting in their own patient, so that we can overcome the problem of rejection. If we are looking at therapies, at transplants, we need to generate large numbers of cells, for instance, in large bioreactors, more on that later. But when we're looking at drug screen or disease modeling, we need high throughput systems. We need to be able to test many different conditions in parallel, but one or the other needs large amounts of cells. When you look at the manufacturing process of a cell therapy product, it follows many of the same steps from a traditional biological product, with a few different, but with a few specifications of their own. We need to generate the cell banks, we need to inoculate the cells, expand them and differentiate them if needed. Then we need to generate the final product, store it, and ship it, and use it for clinical applications. And all this here in the green square needs to be produced under good manufacturing practices. And to give you here an example, if we're trying to produce cardiomyocytes derived from pluripotent stem cells, we need to make sure that they are really cardiomyocytes, they have a high viability, they have their specific potency, for instance, they contract. We need to make sure that they meet the number of those that are needed for a patient. We need to minimize pluripotent cells, which may generate tumors in the patient. We need to remove all these impurities. They have to have a normal number of chromosomes, and they need to be stable for at least 6 months. So these products have a lot of specifications that we need to meet in order to use them in the clinic. So their production, of course, since we need these large numbers of cells, cannot be in the traditional culture place that you use in the laboratory. So we need to use larger systems such as bioreactors. Bioreactors in particular are very important because they offer a 3D environment, which is closer to our physiological one. They are scalable. They can be used at small or larger scales. They provide homogeneity by the impeller. They can be monitors of the conditions inside of them, and these conditions can be controlled. And we can use many different feeding strategies in these bioreactors. Looking at these feeding strategies, for instance, we can culture the cells in a batch system. So we just place the medium at the beginning and then remove it at the end. We can use a repeated batch approach. So for instance, every day we harvest the medium and place new one, but it has a problem. It creates like some zigzag profiles, which you see later. In the fed batch regime, we added concentrated medium to the bioreactor, for instance, every day or even continuously. So we don't remove the medium, instead we keep adding more. And we can also use a continuous approach with cell retention, which is called perfusion. So we are constantly adding new medium and removing the old medium, which is also closer to a physiological environment. So ideally, we want to be able to move through perfusion systems. And how can we culture the cells in the bioreactors? We have essentially 3 approaches: encapsulated in the biomaterial, attached to microcarriers, or as cell-forming aggregates. In the work I'm presenting today, I've cultured the cells as aggregates because the process is overall simple. So we have less materials to work with, so the GMP compliance is easier. The process can also be made cheaper due to the necessity of less materials. And of course, the downstream processing, since we don't have to separate cells from microcarriers, is also easier. But they also come with a few problems themselves. So the aggregates are more susceptible to shear stresses. There can be a large size heterogeneity. So next to the impeller, you can have smaller aggregates, but far away from it, the aggregates can be larger, which is problematic. For instance, for differentiation, we want the aggregates to be at similar sizes. And also, very large aggregates can suffer from diffusion limitations to their center. If you have aggregates with a diameter over 200 micrometers, the nutrients and the oxygen, etc., may not be able to reach the center, and so the cells inside may die or differentiate. So we need to explore bioreactor configurations beyond the normal search tank bioreactor, which can be used in order to minimize some of these disadvantages of the aggregates. And so we have many different bioreactor types that we may be able to use, but we are looking at these vertical wheel bioreactors today. These vertical wheel bioreactors were developed by PBS Biotech, an American company. They are single use, which is great for therapeutic approaches because this minimizes cross-contaminations, and they are available from a 100 milliliter bench scale all the way to an 80-liter production scale. They employ a vertical impeller, so instead of the horizontal one, which is typical of certain bioreactors, they have this wheel which along with the U-shaped bottom of the vessel allows the aggregates to be suspended efficiently and with low shear stress to the cells. And this is very important because pluripotent stem cells in particular are very sensitive to shear stresses. Also, you can see here some computational fluid dynamics images comparing the PBS vertical bioreactor, which is pretty much homogeneous in its agitation, with some spinner flasks which have some clear hot spots next to impeller. And this homogeneity is good not only because it is more sensitive to it's better for shear sensitive cells, but also because it allows the aggregates to be closer together in size. So instead of having very small and very large aggregates, we potentially have aggregates with a much sharper distribution. So they are all pretty much the same size. So we conclude that these bioreactors may be more suited for the culture of pluripotent stem cells over more conventional bioreactor types. So the research questions of this work were if this bioreactor can in fact sustain human-induced pluripotent stem cell expansion, and which are the optimal conditions for this bioprocess. So this is an overall outline of this work. The cells were inoculated as single cells in the 100 milliliter bioreactor. Every day, the cells were sampled in order to assay the growth kinetics, the aggregate sizes, and metabolites and nutrients. And at the end, we harvested the cells in order to check their pluripotency. So these were the first experiments that were conducted using 2 different cell lines. You can see here that, in fact, the cells were able to aggregate. These aggregates grew throughout time and maintained a spherical shape, which is common for human-induced pluripotent stem cells. And you can see here, this is a calcine staining. The cells are green; they stain green. So this means that they maintain their viability throughout the 7 days of expansion. Here you can see the growth curves. So after 7 days, we were able to expand the cells 5-fold. So we had about 70 million cells at the end of the expansion. The aggregates grew throughout time to around 400 micrometers, which might be a little already problematic in terms of diffusion, but with a coefficient of variation at the end between 20 and 30%. This represents the dispersion in aggregate sizes. In both cell lines, you can see that the growth kinetics were pretty similar. Looking at the supernatant analysis, you can see that there was never any significant glucose depletion or any lactate accumulation above inhibitory threshold, which is generally considered to be 20 millimolar. And the yield of lactate from glucose, which indicates the metabolism of the cells, was maintained at the end at about 1.8, which is normal for these kinds of cells. So this all seems very good, but as I mentioned before, in here we use a repeated batch approach. So we every day remove old medium and add new medium. So we create this zigzag profile. So there is this causes a lot of stress to the cells every day when you change the medium, because there is a large variation in the conditions in the vessel. So we try to have a look at a different approach. So instead of using a repeated batch approach, we try to use fed batch. So in this case, instead of just replacing the medium every day, we would add a concentrated supplement. Using this fed batch approach, the aggregates were good form as well. They grew throughout time and they maintained their viability. However, the maximum cell number, curiously enough, was actually a bit lower than with the repeated batch approach. Still, we could obtain about 60 million cells at the end of the expansion. Aggregate sizes and their variation were pretty similar, but when you have a look here at the glucose and lactate concentrations, this variation is much smoother, and again, there was never any significant glucose depletion or lactate accumulation. When we look at the yield of lactate from glucose, curiously enough, at the end of the culture, we start to see a drop. So there might have been a bit of shift in metabolism of the cells. So, but overall, we can conclude that this bioreactor was pretty good for cell growth. However, this large aggregate size still preoccupied us a bit. So we started to have a look at other approaches that we could use in order to reduce aggregate size and also to increase cell viability. And we found a paper at around this time saying that dextran sulfate, which is a molecule which is commonly used in the biopharmaceutical industry for aggregate size control, it could also be used for human-induced pluripotent stem cells. So that's what we tested next. We tried to use the media that we used before in repeated batch and fed batch approach with these dextran sulfates. And in fact, the aggregates could form and they could grow in size and they maintain their viability. So all is good for now. And in fact, we saw that dextran sulfate could improve cell growth twofold. So we could obtain double the cells in comparison to media without dextran sulfate. So by the end of the culture, we could obtain around 140 million cells in only 60 milliliters. And we could do so earlier. So the maximum cell density was obtained at day 7 for media without dextran sulfate. For media with it, the maximum cell density was obtained at day 6 or day 5. However, the other effect we wanted, which was to reduce the aggregate diameter, was actually not obtained. We obtained aggregates with the same diameter at the end, probably due to the even better cell growth. However, the coefficient of variation was a bit lower, although not significantly lower. When we look at the supernatant analysis, at the supernatant profiles, we can see that for the repeated batch medium, which is in orange, glucose depletion was not significant and lactate accumulation was not as well. For the fed batch medium, the glucose almost reached 0. So this means that we may have to have a better refresh rate of the nutrients so the cells don't end up depleted in glucose. Looking here at the yield of lactate from glucose, for the repeated batch medium, it remained at around 1.7, which is normal. But for the fed batch medium, it actually dropped to around 0.7 at the end. And now I'll open here a parenthesis in order to explain the consequences of this. Because proliferative cell types, such as pluripotent stem cells, normally rely on glycolysis in order to obtain their energy and everything they need to multiply. So the yield of lactate from glucose in a glycolytic process is 2. So pluripotent stem cells are normally at around 1.8. But when they start to differentiate, they go back to oxidative phosphorylation profile. So the yield of lactate from glucose drops when they start differentiation. This means that possibly using the fed batch medium, and especially in dextran sulfate, when we have much larger cell densities, we are causing a metabolic shift, which is not as good for the cells. But overall, when you check their pluripotency, for all conditions, the cells maintain the expression of pluripotency markers, as you can see here, by immunocytochemistry, by flow cytometry, by PCR, and also by spontaneous and directed differentiation. So the vertical bioreactors do not compromise the pluripotency of the cells, but when we're going towards high cell densities, we need to be careful with the kind of medium that we use and with the refresh rate of the nutrients. So this table is just here to show you that, in fact, the densities you obtain are very much in the line or better than the densities obtained in other studies. And in fact, looking here, we obtained around 2.3 million cells per milliliter, while this study, which uses perfusion, which is actually a better feeding regime that we want to get to, obtains just a little more, just 2.8 million cells per milliliter. So this approach, the vertical bioreactors and using dextran sulfate, is very good to obtain very high densities of cells. So in conclusion, the vertical bioreactor actually allows for human-induced pluripotent stem cell expansion as aggregates. We can use fed batch, but there is a decrease in cell number. Dextran sulfate can improve this cell expansion a lot, about twofold. We did not observe any differentiation, but fed batch with dextran sulfate might have caused some metabolic shift, which we want to avoid. And of course, if you want to improve cell expansion even further, we might want to have a look at perfusion. Well, this study was performed at 100 milliliter scale, but of course, if we're looking at tissue engineering approaches, we want to go higher. So the work I'm presenting next was not developed by me, but I wanted to show you because it's also interesting we've talked about digital twins a lot today. So I wanted to show you a bit of the work that we've developed in computational fluid dynamics so that we could use what we learned in the culture at 100 milliliters and pass it to 500 milliliters or even higher scales. And why did you use computational fluid dynamics? Of course, we could just use an empirical approach, just go for a 500 milliliter and use trial and error in order to see which were the ideal conditions. However, we would be spending a lot of money, wasting a lot of time. So by using computational fluid dynamics, we can reduce the cost of the scale up. We can test everything much faster. We can obtain the information that we want in realistic conditions, but also in ideal conditions. We can use the conditions that we want. So we first did some tests, some preliminary tests of oxygen mass transfer using the sulfite method. And you can see that the oxygen mass transfer in the vertical wheel bioreactor was larger in comparison to systems of similar volume. Then moving on to the CFD itself, you can see here that the velocity profile in the bioreactor is a lemniscate. That means a figure-8 profile, which allows for a good agitation in the area next to the wheel, but also a bit far away. So there's like this 8 in order to transfer coefficient, and we can see that using CFD
I think we might lose the connection. I think we lost connection. And so we might try to move on.
and overall.
Okay. Diogo?
Yes.
Okay, so we lost a couple of these 2 minutes, the last 2 minutes. So yeah, I'm wondering if you finished.
I'm almost finishing.
Okay, so okay, one more minute, okay?
Okay.
Thank you.
So thank you. So we can conclude overall that these vertical wheel bioreactors show in fact some promise for the large-scale production of cells for biomedical applications. Of course, we need to do some testings in order to see how can you do this scale up, but so far they have shown much promise for production of, for instance, cardiomyocytes or other types of cells, so that you can use for drug screening, disease modeling, or even for direct therapy. So we are not natural Prometheus, but using these vertical wheel bioreactors, maybe one day we can reach a stage where we can in fact regenerate organs at our own will and whenever we need it. So I'd just like to thank my supervisors, all of my group members, all of the funding agencies, and I want to thank you all for being here, and I'm available for your questions. Thank you.
Thank you. Thank you, Diogo, for your so interesting presentation. Let's now move. We have space for one question. Anyone from the audience?
Yes, Professor Mitchell.
Thank you, Professor Mitchell.
It's a very simple observation.
Okay.
You showed lots of pictures where you showed the cells in day 7.
Yes.
And you described all of these as spherical, but all of the images that you showed of dyed cells were not spherical. Is that a consequence of the staining dyeing process? Or are you missing something?
Okay, I think it's a consequence of the staining dye because that dye stains the nucleus, so you don't see the whole cell, you just see the nucleus of the cell, while in the aggregates you can actually, in the bright field images that I showed, you can actually see the whole cell. So I think that's the consequence of the staining itself, and because the aggregates maintain their sphericity. So can we show the... Okay. So I have to go a bit further back. So you can actually see here.
I can see now they're different scales. Sorry, I didn't see that.
They're also different scales. Yes, this is a bit more magnified than that one.
But if you go to another one, there was one which was very like pear-shaped. I was just like these. These are all non-spherical. And another one you had, it was very thick. I'm just trying to understand what the shear effect on the cells is. This is entirely elastic. Which I think you could...
Okay, you're talking about this one. I thought you were mentioning other thing. Yes, this one is a bit pear-shaped because sometimes we have some aggregate fusion. So when I say that aggregates are spherical, I mean like 95% of them maybe, so they're mostly spherical. But sometimes you see some pear-shaped because there's some aggregate fusion. And so when they keep growing, they evolve into a spherical shape. So these might have fused like between day 6 and 7. So they still have this shape, but they go towards a spherical shape because pluripotent cells are small and sticky, so to say. So they go towards a spherical shape with the shear.
But so in the shear, the cells are experiencing a velocity gradient, and the fact they're spherical at the end means that all of that is elastic behavior in the cells. Is that right? So what's the mechanism of it being shear? What's them being shear sensitive?
So why they are shear sensitive? Well, they are shear sensitive because unlike, for instance, bacteria or plants, they don't have a cell wall. So they're all very, they only have like a membrane. So with high shear, they blow up, so to say. So yes, they are small, they are very malleable, they are elastic. So I think that's the reason of their behavior. That's why they are they go towards that spherical shape.
Okay, thank you.
For instance, when we differentiate the cells, they start acquiring other shapes, they get larger, and the aggregates tend to go towards other shapes. They might not be as spherical, but pluripotent stem cells always maintain this shape.
Okay, thank you. Thanks again to Diogo. Thank you very much. So now we are moving on to our next speaker, William Salvador from the University of Lisbon, Portugal. Moving on to our last presentation of this conference. It is entitled Digital Twins for Complex Manufacturing Process on Tissue Engineering. Jeffrey Mitchell, who is the Vice Director of CDRSP and a Coordinator Investigator at the Polytechnic Institute of Leiria, and also an Emeritus Professor at the University of Reading in UK, will join us. He is also a supervisor and supervisor more than 50 PhD and 40 MSc students. Jeffrey Mitchell received the first degree in metallurgy from the City of London Polytechnic and a master in physical research techniques, and also a PhD degree in polymer physics from the University of Cambridge. Thank you, Jeffrey, for also leader and organizing this amazing conference. And thank you also for giving your view on digital twins in a complex manufacturing process. Thank you so much.
This folder, yeah. Mutual resume. You can go real quick. Just make sure that we are sharing our screen. If you wish, you can use it.
Yep. Okay. Thank you. Thank you, Paola, for your kind words. So good afternoon to you all. Thank you for being here.
Thank you.
It's probably time for a cool beer, I suspect. So I want to talk about digital twins. We've heard some things about this today and probably yesterday, and to think about particularly digital twins in complex manufacturing processes. So there's lots of manufacturing processes that we are involved with at the Centre for Rapid and Sustainable Product Development. Some of these are to do with tissue engineering, some are to do with plastics processing, and there's a lot of common features in this. And I want to draw attention to some of these things to help our thinking of how we might develop this area. So this is where we are. This is some of the sorts of things we do, which is sort of complex processing. And so we come to the point of a digital twin. Well, we've heard a whole variety of things. Of course, there are some that will say there's a definition. Everybody has a definition of a digital twin, which is different to everybody else. But I think the things which are in common is that it's a virtual model, which is designed to accurately reflect a physical system. And that physical system could be fitted with various sensors related to vital areas of functionality. And those sensors provide data streams about the different aspects of the physical object's performance. And that data is then relayed to a processing system and applied to the digital copy. Now, of course, having a simulation of something, we've been doing that for tens of years, but in general, a simulation addresses one particular area, and also it doesn't feed back to the physical object. So we can imagine there's a two-way transfer of information, so that the digital twin is guided by the performance of the object, so it can become as accurately reflecting its behavior. But equally, the digital twin then can ask questions of the object and generate new data. So by modifying the performance parameters to do simple experiments to see how it changes and to build up the description and the detail of it. And so it's this two-way process which distinguishes it greatly from simulations. And this is just emphasizing that, of course, models have been around ever since Leonardo da Vinci made one, and simulations have been around ever since we had computers. In fact, simulations existed before computers, but of course they were very simple simulations because the numerical methods available at the time moved rather slowly. But people did have huge arrays of calculating machines and slide rules and things to do particular calculations. So there's nothing particularly new here. But this is something that emphasizes that simulations are usually standalone. So you run it in a computer, you find out something, you plot a graph of performance against some parameter, and that's it. Whereas digital twins are very much concerned with this two-way flow of information that occurs first when the object sensors generate information, and secondly when the insights generated in the process are shared back with the original source object. So that's setting the scene. So multi-scale digital twins or complex digital twins? Well, the most ambitious digital twin, which is being developed at the moment, is the DEFINE project, which is an EU project, which is led by the European Centre for Medium Range Weather Forecasts, which just so happened to be just down the road from where I used to work in the UK. And this is to develop a digital twin that can then be interrogated by very specific applications to answer questions about extreme weather conditions, extreme weather events, to look at climate change and a whole raft of things. So the digital twin is to accurately reflect the planet Earth, and then that can then be interrogated to do that. Now, of course, if you set out to generate a digital twin of the planet Earth, you're going to do it in some discrete way, because otherwise it's an intractable problem. And so when this first realistic climate models were developed in the 1990s, these were on grids, like a finite element grid, but where the grid wasn't a few micrometers, as perhaps we would be familiar in CDRSP, but where these grids were 2 times 300 kilometers. So really quite a coarse range grids. And of course, there's also variations vertically, but we have a coarse range grid there. Whereas in actual fact, the climate models which are informing the Intergovernmental Panel on Climate Change, of which was some results were announced this year, this involves cells which are 100 by 150 kilometers. Now, if you think, okay, that's what we're setting out to do, but now let's just consider one simple, small aspect of something that determines the climate. These clouds, which I realize in Portugal we don't have so many clouds, but these clouds probably cover 25% of the Earth's surface. And so they're an important factor of the balance of transmission of radiation from the sun to the planet Earth, and then the transmission of the infrared radiation outwards into space. And these are formed from ice crystals. So the ice crystals vary in size from a few micrometers to a few millimeters. So already there's a range of scales. But obviously the clouds are large. They can be kilometers, meters, kilometers. But this is all sitting in this climate model that's 100 by 150 kilometers. So this is a very small microscopic detail. And why do we worry about the ice crystals? Well, clouds, when the light comes through them, they scatter the light, they reflect the light backwards, and so it affects the radiation balance on the Earth. And so if you have clouds which are relatively thin, they absorb most infrared radiation that's coming from the planet Earth, but they only marginally affect the incoming sunlight. If you have a cloud which is 100 meters in thickness, it will reflect about 10% of the sunlight that's falling on the Earth, but absorb 50% of the infrared radiation, leading to what we generally call the greenhouse effect. This is what's warming the Earth. And so what's happening to these a few micrometers to a few millimeter crystals in these clouds has a big impact upon the average temperature of the planet Earth. I realize that's a very complicated topic, but it illustrates that in anything, there's a huge range of scales involved. And what we can't do is to have a model of the planet Earth which allows us to identify the individual crystals in these clouds, their position, their rotation, because of course how the crystal affects the incoming light and how it absorbs the infrared radiation depends upon the orientation of the crystals, because it depends upon the orientation of the chemical bonds. And so all of that detail is really important, but can't be incorporated into this large 100 by 200 kilometer scale. I mentioned this not to educate you about climate change models, but to just, it's a very simple example of where we have something that's very multi-scale. And so we have to think about how to handle this process of the crystals. And this is done by using mathematical models that are based upon physical optics and generalized patterns of behavior, which depends upon one or two parameters, such as the density of the cloud and maybe the temperature, because that will also affect the size of the crystals. So then we come to tissue engineering. Tissue engineering is a good example of a manufacturing process, because after all, it's a manufacturing process, which is multi-scale. One of its other characteristics, if we imagine science as a multi-lane highway, tissue engineering is on the inside lane. It's almost falling off the motorway into becoming a failure, because many funding agencies have identified the huge amounts of money that have been spent on tissue engineering with no real viable therapies available. Of course, there are some successes. Quite recently, there was some clinical studies with patients on bone tissue engineering, but in general, it's a poor performing area. So we have to think, how is this transformed? How do we transform it? How do we completely optimize the process so that we can get back into the fast lane and get on to providing a viable therapy? So this shows two things. One, it shows a picture that Jean has already shown earlier in the presentation. This is a picture of a bioreactor. This is one developed at CWSP. This is a scaffold. These are electrodes for electric fields. And then there's material flowing around. It's a complicated object, as is clear. Of course, what do these electric fields do? Maybe they open some channel in a cell. How big's that? Tens of nanometers. This is hundreds of millimeters. So it's a very multi-scale model, in which case it's always going to be difficult to have a fully representative model of every aspect of this, which includes all of the detail, the molecular detail of what happens to the cells, looking at the growth factors and other things included in it, trying to understand the polymer matrix and the influence of the semi-crystalline morphology in the PCL scaffolds, how this impacts on it. So this is, we could think of this as being just as in the same way as a climate model and trying to understand the ice crystals. We need to think of how to handle this. And of course, as we've known, I think we've already seen this slide, this picture earlier on, there are many factors which we need to optimize. There are more factors that need to be optimized than it's possible to think of an optimization strategy for it. So this is a great opportunity for digital twin technology. And as our session chair has said, the use of digital twins in tissue engineering applications is paramount importance to reduce the number of in vitro and in vivo tests. I think probably wasn't said, it was written, but the same thing. So to drive a digital twin, when people think about this in high-level review articles, they think of, this will be solved by having an array of nanoscale sensors that magically tell us all of the things that are going on inside the bioreactor. Of course, some things like the flow conditions, the oxygen levels, nutrient concentrations, pH, temperature, the measurement of electric fields and other things which we heard about earlier on, these are easily measured and digitized using conventional technologies. So this is not the problem. But if we want to know how successful it is in these cells differentiating into a particular cell type or how they're increasing their numbers, then we need to measure other things which are much more difficult to measure. And so if we want to see whether collagen is being developed within the tissue, then we need to identify particular biological sequences. And this sort of work is currently performed using batch processing methodology, so is not particularly suited to a live digital twin model. It could be a digital twin model in which the computer has a time step of a few days, but so it would be rather slow to do that. Now, of course, we can think that there will, over the next few years, be continuing developments in all of the technology that allows us to monitor this, and areas such as microfluidics and real-time PCR, or sometimes called quantitative PCR, will greatly help in providing real-time data, both to do quantitative measurements, also just to indicate whether that particular sequence is present or not. But in other situations, we need to think about where we will get that information. So if we want to know, if the conditions are this, what will be, what's the proportion of collagen being presented, then we need to think about other ways of getting that information. And probably the most satisfactory way of getting that information is for the digital twin to be driven by data that comes from computational models, which can be experimentally validated using 2 or so parameters. So maybe a simple measurement that's possible today in the bioreactor can be used to scale or validate the output of a computational model on the tissue development, the amount of tissue growth, or the amount of collagen that's being generated, or something. And so, because it's important for the digital twin to operate in with real-time data, and then of course in some time in the future, then maybe this sort of gadget, this picture on here, this is a microfluidic device that tells you whether you have sepsis, which is a terrible thing to have, in minutes. Of course, that's not really fast enough for a digital twin, but one can imagine this can be developed further. And so in thinking about the pure form of a digital twin, in which there is simply a system that develops data and the digital twin uses that data, I think we have to think about a digital twin which is driven from both real-time observations and from numerical models based upon experimental data, but where we're looking to perhaps provide slightly lower grade information. And this is not a new idea. And so in terms of thinking about plastics manufacturing, we've already thought about how we can use simulations to provide information for a digital twin. So if you just think of, all the people in the room use 3D printing to make scaffolds. So how digital printers work is important, or how maybe if you use injection molding, and just imagine you have a design of injection molding and you're thinking, perhaps if we just make this part of the cavity a little bit wider, maybe it's much better. But in order to make the cavity a little bit wider, you need to go right back to the beginning and start with a huge bit of metal and carve out the cavity. So that process is on a long time scale, because it's going to take days or months to do, and is not something that you can operate this digital twin waiting for that. And so in that case, it would be very much easier to obtain the consequence of making that gap a little bit wider in a slightly approximate way, but using the output of a injection molding simulation, in which that can be done instantly. Make the gap a little bit bigger, then you have the results, and then that can feed into the process. And so people have suggested this in the past, and so it's possible to envisage this sort of schematic in which this is the real bioreactor, this is the digital twin of the bioreactor, and they communicate via a router, not the sort of router we have in CDSP that doesn't work most of the time, so we can't have Wi-Fi or anything like that. I mean a router that's smart and intelligent and understands, I want to know about something which can be obtained from the library, or it could be something that's obtained from a simulation of tissue development, or it could be something that's taken from the results of batch sampling of the bioreactor, or it could be a multi-scale offline experiment. There's very many resources that could be taken from, and so this could greatly ease the development of effective digital twin systems that describe the whole process of a multi-scale complex manufacturing process. And that's the principal point that I want to present. And so, of course, this still remains like an Internet of Things, but instead of it being an Internet of Things which are sensors that communicate with this, it's an Internet of Things which provide answers to specific questions that the digital twin needs to know, which involve a long time scale to get the absolutely right answer. But if you're thinking you have a plot showing the proportion of collagen fibers that are developing against some process parameter, then whether it goes like that or whether it goes like that, maybe not that crucial. What's important is it's somewhere here, and that information can help optimize the process in a coarse sort of way, which then experiments can refine it slightly more, and in the same way by feeding in other data, you can refine the digital twin to be able to fully replicate the process using a whole variety of data. So to summarize, I think digital twins for any of these multi-scale, and nearly everything is multi-scale technologies such as tissue engineering, climate, plastic processing, and particularly the use of bioreactor systems will, in the optimization of these complex processes, can benefit from the development of a digital twin approach. But we have to accept that at the moment, it's not possible to develop a fully functioning 5-star digital twin in every aspect. And so we think about how practically we have to replace that with the best data that we have at the moment that can be obtained instantaneously, rather than in the next 2 weeks or the next 5 months. It can be obtained now. And I think we'll find that there's a huge amount of data that's available in all of these manufacturing processes to support this. And the simplest thing is if those models have are based upon parameters that come from experimental observation, so that they're sensitive to the conditions and the processing. And of course, to do this, we can only use this route where there's a high level of confidence in the reliability of the simulation, because obviously having the simulation doesn't mean it's right or doesn't wrong. It just tells us that's the answer to whatever the questions we put in. But we need to build up confidence in these sort of sub simulation tasks, so that we can employ them together to run the simulation, and use the digital twin approach to optimize the process. And I think, as we've heard in other ways, that this is a way in which it's possible to move tissue engineering from the very slow lane to the fast lane in a reasonable period of time. Thank you very much.
Thank you, Professor Jeffrey Mitchell. for such an inspired talk. We have time for one question before finishing this session. Anyone from the audience would like to give make a question or a comment?
I have a question. When are we going to have a good network? So we can have an internet of things.
That's a very good question, and I would like to kindly ask the direction board of CDRSP for an answer.
I don't have a question, but just I would like to know your comment about what's the role that you think artificial intelligence can play in all of this, in getting the devices that can respond to the models very quickly, and that you can have everything optimized.
I'm sure there's a big role to play. I think when we know what artificial intelligence is, then we will know that, because I think this is a term that's branded things. When I was as old as you are, artificial intelligence, that was something that used the Lisp programming system, was very much about understanding how machines could talk to humans. Now it's about how machines can listen to humans and learn from them, or listen to other information. And so I don't think there's obviously lots of very simple systems where people have used neural networks or used machine learning that are very simple, but I think calling that artificial intelligence, because the first thing you have to be able to do is to do all of the calculations first. Because if you think, like the other gentleman was talking about, how you optimize something, it's easy to know how to optimize it when you know the answer. If you don't know the answer, it's almost impossible to optimize it, because if you think when what he was talking about, the things which we learned from Sarah Cartmel, if you change the length of the electrode, which might appear to be some inconsequential effect, then this changes the amount of hydrogen peroxide produced. And this is something that's perhaps not in the model. You know, I mean, maybe a few years ago it's not in the model, and then people are doing rather poor experimental practice, having different electrode lengths, and so seeing a big change. Whereas once you realise this is important, then it's easy to have the intelligence to keep all these things, these fixed, and have a better idea. And I think I think this is a big problem in science, because I've always sort of had the view science is like being on a big island, and the island has cliffs all the way around it. So if you step over the line, you fall down, and you find the solution. Right? How do you find that edge? Well, you can walk around in circles for days, unless you have a methodology to find the edge, and you're patient enough to find the edge, because maybe you need to walk in straight lines. You guess the size of the island, and then you walk in a straight line for 5 kilometers, and if you haven't fallen over the edge, you know you've got the first estimate wrong. And I think it's easy to think of the idea, but I think we perhaps, I don't mean there aren't people who know what artificial intelligence is. I'm saying I don't know what artificial intelligence is or how to make use of it, but I can imagine it's a powerful computational tool that will prove to be invaluable when we're looking for patterns of behavior in data, for example. So if you imagine something like this, where you can do millions of experiments bearing all these parameters, you could just do all of these experiments, doing them in a very methodical way. Just imagine the problem: logbook after logbook after logbook. How will you find the solution? But if somehow this is in some digital system in which it's possible for the system to look for patterns of behavior, then this could very rapidly get to the point where the human can then look at the same data and think, oh, now I understand it. So it's a tool to help us find the solution from very complex information.
Yeah, I was asking this because now a lot of current researchers and recent review papers on bioreactors and bioprocessing are bringing the artificial intelligence into the mix. So that's why.
Yeah, but they don't say what they will do.
Yeah, okay.
I think that's so what will happen.
Yeah.
And so there's some software that's used, and what does the software do? How does it work? I think we have to be not cautious of it. We need to embrace this, but we need to embrace it in a way that we're in charge and we're understanding it. Otherwise, it's another black box.
Yeah, I agree.
We're pressing the button.
Thank you.
Okay, thank you, Paola.
Thank you, Professor Jeffrey. If you would like to say some final words or remarks to
Yes.
to end the conference.
Yes, no, I can do. Thank you very much. So, firstly, thank all of the 34 people who are still here. So thank you, but we've had many people from many different countries from around the world online. Of course, we don't really see them in here, but if we've been online, we would see where they come from, and that's a very useful part, and part of, as I said when we listened to Siran Ramakrishna, he's a very good example of somebody who's passionate about science and about ensuring that you understand what he says. So he puts a lot of thought into what the questions he's asking and the answers he's providing and the illustrations and such things, so that we can all understand it. And that's what we all need to do, because otherwise, if we just have the answer, so if William has the answer how to make zillions of cells, but he doesn't tell anybody, he's the only person who benefits from it. You know, and that's obviously a key part of science. And so this conference is designed so that anybody can attend. There's no penalty to face if you attend. You can be anywhere. You don't have to pay any traveling costs. You don't have to pay for a hotel, and you don't have to pay for a registration fee. Do you understand why conferences have registration fees? You go to a conference and they say, I want 450 euros for you to register. Why? Because somebody's running a business that's making it. They're not trying to communicate science. They're trying to make a business. And so we as scientists need to fight against that move, because after all, it's our knowledge, our understanding that we're either trying to improve or we're trying to spread out to other people. Of course, a conference like this is nothing without an audience, but it's also nothing without speakers and without session chairs. So, disappeared. Thank you, Paola, and all of the other session chairs for doing a very good job. We've kept very well to time, except for this afternoon. So you don't get it back.
No. Let me correct you, because on the program we say that the close of the conference is at 5:20 and it's now 5:22.
All right. Okay, very good. And so
excellent share, by the way.
Yes.
Excellent time.
I think
management.
probably that was because you had somebody very good in the middle who recovered the time. But we also need to thank Artur, Daniel, Renato, Thomas, somebody else, Andrea, yeah, I think, for ensuring that as far as possible we have no technical interruptions and such things. Clearly there's a big message for the direction board to improve the reliability of the network. I'm told that last week some new software was installed in the servers in the building, and it may well be that's a typical cause of problems if you have something new. And so maybe if we were to revert to the old software, it might be better. but it's very good. The conference proceedings will be published in a volume of a series, which is a CBRSP conference proceeding series, and we will try to do that as quickly as possible. It will have an ISBN and it will have a DOI, and when we have it assembled, we will send the information to Scopus for it to be indexed, because we're not in charge of Scopus, so it's difficult to know whether it will be indexed, but of course it will be registered as a publication, and so I think for most uses of it, it will serve as an outcome. But so thank you very much for being here and participating and asking questions. And of course, the key thing to do now is to go away and do something with something you've learned. Otherwise, it was pointless. We spent a nice 2 days together doing something, but what are we going to do? What are we going to do next week that's different to what we would have done anyway?
Internet.
Hardware. I know that, but that's not something we've learned that, but we knew that beforehand, if we were honest.
Yeah.
And so we need to think about how we can use the knowledge that we've gained, how the knowledge we've learned about the paddle wheel bioreactors, for example, how are we going to use that? Do we just think, oh, it was very interesting, or do we think, oh, this is really interesting, perhaps we should be thinking about making such a bioreactor? I don't know, but that's, I would say, taking action on what we've learned will be very important. So thank you.